Hello there, and welcome to the Calm Science Sleep channel. I'm Jeffrey, and so glad you found your way here tonight. Maybe it's been a long day, or maybe you're simply the kind of person who finds it easier to let go of the world when your mind has something quiet and vast to wander through. Either way, this is exactly the right place to be. There's nothing left to do now, nothing to finish, nothing to check, nothing to hold on to. Just let your body settle and your breathing slow and allow yourself to drift. Because tonight, we're going on a journey, not a hurried one, not a dramatic one, just a long, gentle drift through the universe. We'll move the way light moves, steadily and without effort, touching one world and then another, passing through star fields and quiet moons, through ancient light and slow-spinning galaxies, through all the strange and beautiful things that fill this vast and patient cosmos. We'll let the facts come softly, one at a time, like stones dropped into still water, each one sending out its own quiet ripple before the next arrives. Some of what you hear tonight you may already know. Some of it may arrive as something new, and some of it may simply float past like clouds on a still afternoon, peaceful, unhurried, and just interesting enough to carry your thoughts gently away from whatever is waiting on the other side of sleep. And if these calm journeys through science and space help you rest, consider liking and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time. Now, let's begin. We start tonight where all journeys eventually lead, with light. Right now, the light reaching your eyes, if you were to step outside and look up, left those stars years ago. Some of it left decades ago. Some of it left thousands of years ago, long before any human civilization had learned to write down what it saw. When you look at the night sky, you are not seeing the universe as it is. You are seeing it as it was. A gallery of different moments, all arriving at the same instant. The star you see in one part of the sky may be showing you something that happened 100 years ago. The dim smudge in another part might be sending you light from 1,000,000 years past. There is a kind of peace in that, if you let it settle. The universe doesn't rush. Light travels as fast as anything can travel, and still it takes years, centuries, millennia to cross the distances between stars. You, lying still right now, are receiving ancient messages from the cosmos. Not through any instrument, just through the simple fact of existing on a planet with clear nights and open skies. The nearest star to our sun is called Proxima Centauri. It sits about 4¼ light years away, which means the light from it that reaches us tonight left its surface 4¼ years ago. To reach the next nearest star system after that, you would need to travel more than 6 light years. And this is just our immediate neighborhood, the quiet cul-de-sac at the edge of a galaxy containing over 100 billion stars. The Milky Way itself stretches roughly 100,000 light years from one side to the other. If you were somehow able to travel at the speed of light, it would still take you 100,000 years to cross it. To put that in human terms, 100,000 years ago, our ancestors were living in small groups, navigating Ice Age landscapes, and looking up at the same Milky Way we see today. The galaxy was ancient then too, and it will be ancient long after we are gone. But here's the thing about the Milky Way that most people don't fully feel when they hear it. We are inside it. We cannot step outside and look down at its beautiful spiral shape the way we see photographs of other galaxies. Those images, the graceful pinwheel arms, the glowing core, the faint outer wisps, all of that is how we imagine the Milky Way looks from a distance. From inside, we see it differently. We see a band of light stretching across the sky, pale and soft on a dark, clear night. A river of countless overlapping stars, too numerous and too distant to separate with the naked eye. We are embedded in the disk, looking along it, the way you might stand in a forest and look along a line of trees, unable to see the forest's full shape from within. It took centuries of patient astronomy before humans understood that this pale stripe overhead was actually the compressed edge-on view of our own galaxy. William Herschel, in the 18th century, tried to map the Milky Way by counting stars in different directions, reasoning that the galaxy extended furthest in the directions where he could see the most stars. His map was roughly correct in shape, but deeply wrong in scale, and it placed the sun near the center. It wasn't until the early 20th century that the American astronomer Harlow Shapley, studying the distribution of globular clusters, recognized that the sun was nowhere near the center. We live in the outer reaches, in a quiet spur of stars about 26,000 light-years from the galactic core, out here in the calm. And that calmness may be one of the reasons life had a chance to develop here at all. The center of the Milky Way is not a peaceful place. Near the core, stars orbit in tight, fast loops, jostling close together in a region dense with radiation and gravitational chaos. At the very heart sits Sagittarius A*, the supermassive black hole that anchors the entire galaxy. It holds more than 4 million times the mass of our Sun, compressed into a space smaller than the orbit of Mercury. Astronomers have watched the stars near it for decades, tracking their paths as they swing around the invisible center of gravity. Some of these stars whip past at speeds of thousands of kilometers per second, completing full orbits in just a few years. Their motion reveals the presence of something neither they nor we can see, a singularity, a place where the known laws of physics compress into a single, unresolvable point. For now, Sagittarius A* sleeps. It occasionally flares when gas or dust falls inward, brightening briefly in X-rays before fading again. But long ago, it may have been something far more dramatic. Evidence suggests that millions of years past, the galactic center erupted in a tremendous outburst, perhaps when a large cloud of gas fell into the black hole all at once. The energy from that event may have carved the enormous gamma-ray structures now called the Fermi bubbles, two vast lobes of high-energy light rising tens of thousands of light-years above and below the galactic plane, invisible to the naked eye but unmistakable to telescopes tuned to the right frequencies. They are still there, drifting silently above and below us, like a memory the galaxy hasn't quite finished exhaling. From our quiet corner in the Orion Spur, tucked between the larger Sagittarius and Perseus arms, we orbit this center, without ever coming close to its violence. It takes our solar system about 225 million years to complete a single orbit around the galactic core. Astronomers sometimes call this span a cosmic year, or a galactic year. In all of the sun's 4.5 billion years of existence, it has completed only about 20 of these immense loops. when the first dinosaurs appeared on Earth, our solar system was in a completely different part of the galaxy. When it completes another full orbit from now, Earth as we know it will have changed beyond recognition, and all the while we drift, quietly, steadily, without feeling any of it. Let your breathing slow a little more now. There's no need to hold any of this tightly. Let it simply pass through. The spiral arms of the Milky Way look like fixed structures when we see illustrations of them. Great sweeping curves of stars and light. But they are not fixed at all. They are patterns, density waves moving slowly through the disk, like ripples in a pond, or the compressed bunching of traffic on a highway where cars slow down without stopping. As these waves move through the interstellar medium, they compress gas and dust, triggering new stars to form. The bright young stars light up the wave's position, making the arm visible. But those stars were not born in the arm, and they will not stay in it. They drift through over millions of years, and new stars form in their place. The arms are a moving pattern, not a moving object. A slow and elegant illusion maintained by gravity and time. Our sun is part of this flow. It moves in and out of these density patterns across its long orbit. Right now, we sit in a relatively quiet stretch, and this too may matter for life. Every time the solar system crosses a spiral arm, it enters a region of higher star density, more frequent supernova, more intense radiation. The gaps between arms are calmer, safer, more conducive to the long, stable stretches of time that complex life seems to require. Earth has had billions of years of relative cosmic quiet. That may not be coincidence. Now let's drift outward, away from the disk, away from the bright plane of stars, into the halo. The halo of the Milky Way is one of the least known parts of the galaxy, and one of the most important. It is a vast spherical region surrounding the disk, extending far beyond the outermost spiral arms, thin and mostly invisible, but full of meaning. It contains ancient globular clusters, tight spheres of hundreds of thousands of old stars orbiting the galactic center in long elliptical paths. Some of these clusters are more than 12 billion years old. Their stars are metal poor, meaning they formed before earlier generations of stars had time to forge and scatter the heavier elements. They are fossils of the early cosmos, time capsules drifting in the dark. The halo also holds stellar streams, long ribbons of stars that were once part of smaller galaxies. Those galaxies wandered too close to the Milky Way, were caught in its gravity, and were slowly pulled apart. Their stars now trace the paths of their former orbits like ghostly signatures across the sky. Astronomers can detect these streams with precise instruments, tracing the paths of ancient mergers that happened billions of years ago. The galaxy, it turns out, is built from the ruins of other galaxies. Not a single pristine object, but a layered composite, stitched from collisions and absorptions and slow gravitational dismemberments across deep time. The largest component of the halo is invisible, dark matter. This mysterious substance, still unknown in its true nature, surrounds the galaxy in an enormous cloud that extends far beyond even the farthest halo stars. It exerts gravity. It holds the Milky Way together. Without it, the galaxy's outer regions would be spinning too fast to remain bound, and stars would be flung into intergalactic space. With it, the math works. The rotation of the galaxy makes sense. The large-scale structures of the cosmos fall into place. And yet, we cannot see it, cannot touch it, cannot detect it directly with any instrument we currently possess. We know it only by its effects, the way an invisible hand is known by the things it moves. There is something quietly humbling in that. The majority of what holds our galaxy together, what holds us in place, is something we do not understand. The universe is full of presence we cannot see. Let that thought settle like a stone into still water. Let it carry you a little deeper. Now let's leave the Milky Way for a moment and drift further out. Step back far enough, and the Milky Way is no longer a band of light across the sky. It becomes a small glowing disk, one galaxy among many, drifting through a cluster of galaxies called the local group. The local group spans more than 10 million light-years and contains more than 50 galaxies. Most are small and faint, dwarf galaxies with far fewer stars than the Milky Way. Some barely more than loose handfuls of ancient suns. But two large spirals dominate the group: the Milky Way and Andromeda. Andromeda is our nearest large galactic neighbor, lying about 2.5 million light-years away. On a clear, dark night in the northern hemisphere, you can find it with the naked eye, a soft oval smear in the constellation of that name, one of the most distant things visible without any instrument. That faint blur is 2.5 million light-years away. The light entering your eye left it long before modern humans existed. And despite that distance, Andromeda is moving toward us. In about 4.5 billion years, the Milky Way and Andromeda will merge. This sounds violent, but in practice, it'll be stately and slow. The two galaxies will pass through each other, their gravity stretching both into long curling arcs of stars. Tidal tails will sweep outward. The supermassive black holes at each center will eventually spiral toward each other and merge. Over billions of years, the two spirals will blend into a single larger elliptical galaxy. Astronomers sometimes call this future galaxy Milkomeda. Stars themselves will almost never collide during this process. Space is too empty even inside a galaxy for that. But the shapes will transform. What we know as the Milky Way, the band of light crossing our sky, the graceful spiral, will cease to exist. Its stars will remain, scattered into new orbits in a new, larger system. Nothing will be lost, only rearranged. Even galaxies are not permanent. They evolve, merge, and become something else over time. And the local group itself is just a small node in something larger. The local group belongs to a supercluster called Laniakea, a vast structure of galaxies stretching 500 million light-years across. And Laniakea is just one feature in the cosmic web, the largest structure in the known universe. Filaments of galaxy clusters stretch between enormous voids, forming a pattern that resembles, in some photographs, the branching structure of neurons in the human brain. Whether that resemblance means anything is uncertain. But the fact that the universe's largest structure and the brain's internal architecture share a similar pattern is quietly strange and beautiful. In the voids between those filaments, almost nothing exists. Vast regions of space, hundreds of millions of light-years across, containing very few galaxies, very little gas, very little of anything. These are the quietest places in the universe, darker and emptier than we can quite imagine. if you lived in a galaxy inside one of those voids and looked out, you would see almost nothing in any direction. No neighbors, no star fields, just the faint microwave glow of the early universe and the distant light of clusters far beyond the void's edges. We do not live in such a void. We live in a relatively populated neighborhood, but the voids remind us that emptiness is one of the universe's primary features. Most of it, by volume, is simply space. Now let's come back. Come back from the filaments and the voids. Come back to our galaxy. Come back to our solar system. Let the distance close gently, like a lens slowly narrowing its focus. Here is our sun, a middle-aged star, unremarkable among the 100 billion stars of the Milky Way, and yet the source of almost all the energy that sustains life on Earth. The sun is about 4.5 billion years old and is roughly halfway through its expected lifetime. It burns by fusing hydrogen into helium in its core, releasing enormous energy in the process. Every second, it converts about 4 million tons of its own mass into pure energy. And yet, it is so vast that this loss barely registers against its total mass. It will continue burning steadily for another 5 billion years or so before running low on hydrogen fuel. When that happens, the sun will change. It will expand into a red giant, swelling outward until it likely engulfs the inner planets. Then it will shed its outer layers in a glowing shell of gas called a planetary nebula, and the dense core that remains will become a white dwarf, roughly the size of Earth, but containing most of the sun's mass. This white dwarf will radiate its remaining heat slowly into space over trillions of years, fading from glowing white to dim yellow to cold black, becoming at last a dark remnant drifting through the galaxy with no light of its own. But that is a long way away. Tonight the sun is steady. It is warm and familiar and necessary. Now let's visit the planets, not quickly, slowly, one by one, letting each one rest in your mind for a moment before we move on. Mercury is the innermost planet, the smallest of the rocky worlds, and the fastest in its orbit, completing a full trip around the sun in just 88 Earth days. But it spins slowly, so a single day on Mercury, from one sunrise to the next, lasts about 176 Earth days, longer than its year. On the sun-facing side, temperatures climb above 400 degrees Celsius. On the night side, they drop to nearly -200. There's almost no atmosphere to spread the heat, just an exosphere, a near vacuum of atoms blasted from the surface by solar wind, too thin to protect, too thin to hold warmth. Inside Mercury, something unexpected, a core that makes up roughly 80% of the planet's radius, far larger in proportion than the cores of other rocky planets. One leading theory suggests that early in the solar system's history, a massive collision stripped away much of Mercury's outer layers, leaving the dense metallic core as the dominant feature. If that's true, Mercury is essentially a planetary remnant, a core with a thin veneer of crust, a survivor of ancient violence. And yet, tucked inside permanently shadowed craters at Mercury's poles, water ice persists. Craters so deep that sunlight never reaches their floors, even on a planet this close to the sun. There, temperatures remain cold enough to preserve ice that may have arrived billions of years ago from comet impacts. In the most sun-baked world, ice hides quietly in the dark. Venus comes next, the second planet, and in many ways, Earth's strange twin, almost identical in size and mass, but utterly different in character. Venus rotates in the opposite direction from most planets, slowly, so slowly that a Venusian day is longer than its year. The sun rises in the west and sets in the east. Its thick atmosphere, composed mostly of carbon dioxide with clouds of sulfuric acid, creates a greenhouse effect so extreme that surface temperatures reach over 460 degrees Celsius, hot enough to melt lead. The hottest surface of any planet in the solar system, despite Venus being farther from the sun than Mercury. It was not always this way, perhaps. Some scientists believe Venus may have once had liquid water on its surface, may have once been something closer to habitable, before its atmosphere thickened and its oceans boiled away over billions of years. A possible cautionary version of Earth's future, or a reminder that the line between habitable and hellish can shift given enough time and the right or wrong atmospheric chemistry. We do not linger on Venus. It does not invite lingering. Earth. There is not much to say about Earth that you don't already know from living on it. But sometimes the familiar deserves a moment of quiet attention. Earth is the densest planet in the solar system. It is the only one with plate tectonics, the only one where water exists in all three states simultaneously, and as far as we know, the only one where life has taken root. Its magnetic field, generated by the churning of molten iron in its outer core, shields the atmosphere from the solar wind. Its moon, unusually large for a rocky planet, stabilizes Earth's axial tilt, keeping the seasons regular and the climate relatively stable over long periods. From space, Earth is mostly blue. The oceans are vast. The atmosphere is thin, just a shell of air and cloud barely visible against the darkness. And yet, that thin shell is everything. The oxygen in it was produced by billions of years of photosynthetic life. The rain that falls from it cycles water that has been in circulation since the planet was young. The atmosphere is not just a layer around a rock. It is a living system, shaped by and shaping the life within it. You are part of that system. Right now, breathing quietly. The moon rests nearby. Roughly a quarter of Earth's diameter, large enough to be considered a double planet by some standards. It is slowly drifting away from us, about 3.5 centimeters farther each year, pulled outward by the same tidal forces that once brought it into a stable orbit. Long ago, it was much closer, and the tides it raised on Earth's young oceans were tremendous. Its gravity has helped slow Earth's rotation to the comfortable 24-hour day we experience now. It has steadied our axial tilt, kept the seasons predictable, and made the world a quieter, more stable place. The surface of the moon changes almost not at all. No wind, no rain, no plate tectonics. The footprints left by Apollo astronauts in the 1960s and 1970s will remain undisturbed for millions of years. The craters formed by ancient impacts are still there, unchanged, a record of the solar system's chaotic early history preserved in silence. The moon is not just a companion in the sky, it is an archive. Mars is next, the red planet. That redness comes from iron oxide coating the surface, the same compound that turns iron red when it rusts. Mars is cold and thin-aired, its atmosphere less than 1% as dense as Earth's, mostly carbon dioxide, too thin to breathe, too thin to retain much heat. Temperatures can drop to -120 degrees Celsius at the poles, in winter. And yet Mars has some of the most dramatic geology in the solar system. Olympus Mons, the largest volcano, rises nearly 22 kilometers above the Martian plains, almost 3 times the height of Everest. Valles Marineris, the Great Canyon system, stretches more than 4,000 kilometers across the equator and plunges 7 kilometers deep in places. It would span the continental United States. Mars also shows the scars of a wetter past. Valley networks carved by ancient rivers, delta formations where water once spread into standing bodies, minerals that form only in the presence of liquid water. Billions of years ago, Mars may have had an ocean in its northern hemisphere, rivers flowing across its southern highlands, a world where life, if it had taken hold, might have had a foothold. What happened to that water is still not fully understood. Some is locked in ice at the poles and beneath the surface. Some escaped into space when Mars lost its magnetic field and its atmosphere thinned. The full story remains unfinished. Somewhere between Mars and Jupiter, the asteroid belt drifts, not the dense obstacle field of science fiction, but a vast and mostly empty region containing millions of rocky bodies separated by enormous distances. If you were to fly through it, you would almost certainly see nothing. The average distance between asteroids is measured in hundreds of thousands of kilometers. The total mass of the entire belt is less than 5% of the Moon. It is the raw material of a planet that never quite came together, scattered by Jupiter's powerful gravity before it could accrete into a single world. Some asteroids carry their own moons. Some are rubble piles, held together only by their own weak gravity, loose collections of rocks and dust that would crumble under the pressure of a human hand. Some may harbor water ice in their interiors, or carbon-rich minerals, or metals in concentrations that dwarf anything in Earth's crust. And then Jupiter. Jupiter is a world so large that it defies easy comparison. More than 1,000 Earths would fit inside it. It contains more mass than all the other planets combined, more than twice over. Its gravity dominates the outer solar system, shaping the orbits of asteroids and comets, flinging some inward toward the inner planets and sending others out into deep space. It may act as a partial shield for the inner solar system, its gravity intercepting some of the comets and asteroids that might otherwise strike Earth. The Great Red Spot is a storm that has been raging in Jupiter's atmosphere for at least 350 years, possibly much longer. It is wide enough to contain 2 Earths inside it. The winds along its outer edges exceed 400 kilometers per hour. And yet, even this immense storm is slowly shrinking. Scientists watch it with each pass of our telescopes, wondering whether it will eventually dissipate or stabilize or simply contract into something smaller, but no less fierce. Jupiter has more than 90 moons. 4 of them are large enough to be worlds in their own right, discovered by Galileo Galilei in 1610. The first objects in our solar system found to orbit something other than Earth, a discovery that helped overturn the idea that everything in the heavens revolved around our world. Io, the innermost of the 4 Galilean moons, is the most volcanically active body in the solar system. Tidal forces from Jupiter's gravity squeeze and flex Io's interior, generating enormous heat. Its surface is covered in active volcanoes, some sending plumes hundreds of kilometers into space. The landscape is young, constantly reshaped, painted in vivid sulfurous yellows, reds, and blacks. Europa is quieter on the outside, but more intriguing beneath. Its surface is a shell of cracked ice, crossed with dark lines and ridges that suggest movement, shifting, the influence of something liquid below. And below, evidence strongly suggests, lies a vast ocean of salt water kept liquid by tidal heating. That hidden ocean may be larger than all of Earth's oceans combined, and within it, where warm water meets the rocky seafloor, there may be hydrothermal vents, places where chemistry is rich and energy is available. On Earth, such vents support entire ecosystems independent of sunlight. The possibility that something similar might exist in Europa's dark subsurface ocean is one of the most quietly exciting questions in planetary science. Ganymede is the largest moon in the solar system, larger even than the planet Mercury. It has its own magnetic field, the only moon known to possess one, generating shimmering auroras in its thin atmosphere. Callisto, the outermost of the four, is ancient and heavily cratered, its surface largely unchanged for billions of years, a quiet archive of early solar system bombardment. Let's move further out still. Let the distances lengthen. Let the temperature drop and the light fade. Saturn. There is almost nothing in the solar system that looks quite like Saturn. From a distance, the rings appear solid, a gleaming sheet of material circling a pale cream-colored planet. But they are not solid at all. They are made of countless individual particles, mostly water ice, ranging from grains of sand to house-sized chunks, each one orbiting Saturn on its own path, kept thin and flat by the planet's gravity and the influence of small shepherd moons that guide the ring particles and carve gaps between the bands. The rings stretch more than 280,000 kilometers from one side to the other, yet in most places, they are less than 100 meters thick. Hold a sheet of paper sideways and imagine it scaled up to the size of a continent. That is roughly the proportion. From a distance, they look permanent. From up close, they are delicate, constantly shifting, their particles jostling and colliding in slow motion. The whole structure maintained by the precise balance of gravity and orbital mechanics. The Cassini spacecraft orbited Saturn for 13 years, from 2004 to 2017, sending back extraordinary detail. It found that Saturn's rings are likely only a few 100 million years old at most, young by planetary standards. They may have formed when a large icy moon wandered too close and was torn apart by tidal forces. The rings are slowly disappearing, material drifting inward along magnetic field lines and falling onto Saturn as ring rain. In another 100 million years or so, they may be gone. We happen to exist at the brief moment in the solar system's history when Saturn wears this spectacular crown. Saturn's largest moon, Titan, is a world of strange familiarity. It has a thick atmosphere, mostly nitrogen, thicker than Earth's. It has weather, including rain, rivers, and seas. But on Titan, the liquid is not water. It is methane and ethane, hydrocarbons that fall from the orange haze as rain and pool into lakes and seas near the poles. The Huygens probe, dropped from Cassini in 2005, descended through Titan's atmosphere and became the first spacecraft to land on a moon in the outer solar system. It recorded wind sounds and chemical data and photographed a landscape of rounded pebbles of water ice sitting in what appeared to be a dry riverbed, shaped by flowing liquid, long since evaporated. Titan is a moon with a weather system, a hydrological cycle, and probably a subsurface ocean of water, one of the most complex and alien environments in the solar system. Enceladus, another of Saturn's moons, is smaller but no less remarkable. From its south pole, enormous geysers erupt through cracks in the ice, spraying water vapor and particles into space. Some of this material feeds Saturn's outermost ring. The Cassini spacecraft flew through these plumes and detected organic molecules, hydrogen, and signs of chemical reactions consistent with hydrothermal activity on the seafloor. Enceladus is tiny, barely 500 kilometers across, and yet it may harbor one of the most habitable environments in the solar system, a warm ocean beneath ice, venting chemistry into space. Its geysers are, in a sense, the moon offering its own subsurface ocean up for analysis, an invitation. Now Uranus. Uranus is tipped. It rotates on an axial tilt of 98 degrees, meaning it essentially rolls along its orbital path on its side, its poles pointing roughly toward and away from the sun during parts of its orbit. One pole receives 42 years of continuous sunlight, then 42 years of darkness. The cause of this extreme tilt is not fully known, but the leading theory suggests a massive impact long ago knocked the planet onto its side and left it rolling. Uranus is cold, the coldest planetary atmosphere in the solar system, despite not being the farthest planet, with temperatures dropping to negative 220 degrees Celsius in its upper clouds. It glows a pale blue-green, the color coming from methane in its atmosphere, absorbing red wavelengths of sunlight and reflecting blue and green. It has rings, narrower and darker than Saturn's, discovered in 1977, when they were seen to block starlight during an occultation. And it has moons, with names drawn from Shakespeare, Ariel, and Umbriel, Titania, and Oberon. Miranda, with its extraordinary cliffs and fractured terrain, suggesting a past of geological upheaval. Voyager 2 is the only spacecraft ever to visit Uranus, flying past in January 1986 and returning images of a quiet, featureless blue-green disk. The planet gave away very little. It remains one of the least understood worlds in the solar system. Neptune is farther still, pale blue and stormy. It receives less than 1,000th of the sunlight that Earth does, yet it has the fastest recorded winds in the solar system, exceeding 2,000 kilometers per hour. This energy comes not from the sun, but from within. Neptune radiates significantly more heat than it receives, driven by some internal process we do not fully understand. Neptune was not discovered by looking. It was discovered by mathematics. In the 1840s, astronomers noticed that Uranus's orbit contained small, unexplained deviations, as if something were pulling it off course. Two mathematicians working independently, Urbain Le Verrier in France and John Couch Adams in England, used those deviations to calculate where an unknown planet must be. When astronomers pointed their telescopes at Le Verrier's predicted position, Neptune was there. It was the first planet found on paper before it was seen through glass, a triumph of mathematics over mystery. Neptune has a large moon called Triton that orbits backward, moving opposite to the planet's rotation. This retrograde orbit strongly suggests that Triton did not form around Neptune, but was captured from the outer solar system, likely from what we call the the Kuiper Belt. The capture must have been violent, disrupting Neptune's original moons. Triton itself is geologically active, with nitrogen geysers erupting from its frozen surface, driven by the faint warmth of distant sunlight heating dark patches on the ice. Triton is slowly spiraling inward. In roughly 3.5 billion years, it'll come close enough that Neptune's tidal forces will tear it apart, creating a ring system that may rival Saturn's in its brief glory. A moon becoming rings, a kind of recycling on a scale too large to quite comprehend. Beyond Neptune lies the Kuiper Belt, a wide disk of icy bodies extending billions of kilometers from the Sun. This is where Pluto lives, reclassified as a dwarf planet in 2006, but no less fascinating for the change in label. The New Horizons spacecraft, which flew past Pluto in 2015, revealed a world of surprising complexity. Mountains of water ice rising kilometers above the surface. Nitrogen ice plains smooth enough to suggest recent geological activity. A heart-shaped basin, Sputnik Planitia, so large and so bright that it instantly became one of the most recognizable features in the outer solar system. And hints, strong hints, of a subsurface ocean of liquid water beneath Pluto's ice, kept liquid by the slow decay of radioactive elements in the rock below. Pluto, cold and distant and small, hiding an ocean. Beyond the Kuiper Belt, the solar system grows quieter still. There is thought to exist a vast shell of icy bodies, the Oort cloud, stretching nearly a light year from the Sun, the likely source of long-period comets that occasionally fall inward on lonely elliptical paths and grow brilliant tails near the Sun before returning to the dark. The Oort cloud has never been observed directly. We know it only from the comets it sends us, distant messengers from the solar system's cold outer memory. At the edge of the Oort cloud, the Sun's gravitational influence fades into the interstellar medium. This is where Voyager 1 travels now, launched in 1977, crossing the boundary into true interstellar space in 2012. It is the most distant human-made object ever built. At the time of this recording, it is more than 23 billion kilometers from Earth. Its signal, traveling at the speed of light, takes more than 20 hours to reach us. It is powered by a small nuclear battery that slowly loses strength, and engineers on Earth have had to carefully deactivate instruments one by one to keep it functioning. Someday, within the next decade or two, it will fall silent. But by then, it'll be so far away that it barely matters. It is already beyond reach, already a message cast into the void, still transmitting, still whispering back to us across the dark. Aboard Voyager 1 and its sister spacecraft, Voyager 2, is the Golden Record, a 12-inch gold-plated copper disc designed by a team led by Carl Sagan, containing sounds and images meant to represent life and culture on Earth. It includes greetings in 55 languages, music from around the world, the sounds of surf and rain and wind, a mother's first words to her newborn child, the brainwaves of a young woman in love, a diagram of a human form, coordinates pointing back to our sun. It is addressed to whoever or whatever might someday find it. It is the most optimistic message ever sent. It will drift through interstellar space for millions of years before coming close to another star. It is a small gold disk floating in the dark. And somehow that feels like exactly the right gesture. We have now traveled far tonight. From the Earth beneath you, outward past the planets, through the asteroid belt and the gas giants and the ice worlds and the distant belt of frozen relics. We have reached the edge of the sun's domain, touched the boundary where solar wind gives way to the thin gas between stars. Now let's drift upward, out of the plane of the solar system, away from the bright disk of the Milky Way, out into the halo. From here, the galaxy is a glowing disk below, lit from within by stars, its spiral arms tracing faint patterns of brighter and dimmer light. Above and below it, the halo stretches in all directions, its ancient stars scattered wide and thin, its dark matter invisible but everywhere. The local bubble around our solar system, a region of warm, thin gas carved by ancient supernova, glows faintly in ultraviolet. The nearby dwarf galaxies drift in their slow orbits, the Magellanic clouds visible as smudges of light trailing their streams of stripped hydrogen into the dark. And then further, the local group comes into view. Andromeda, off to one side, similar in size, its own spiral structure dimly visible. A scattering of smaller companions around both great spirals, all of them moving with the slow shared drift of the group. Further still, the local group is a dot in the Virgo supercluster. The Virgo supercluster is a spur in Laniakea. Laniakea is a concentration in the cosmic web, and the cosmic web stretches in all directions, its filaments connecting clusters of galaxies separated by voids so large that the word vast is not quite adequate for them. Somewhere in all of this, your body is at rest on a small blue planet orbiting an ordinary star in the outer reaches of a spiral galaxy that is itself just one of perhaps 2 trillion galaxies in the observable universe. 2 trillion galaxies, each one containing billions or hundreds of billions of stars. The numbers exceed anything the human mind was built to hold. And yet, here you are, and here I am. And between us, for this little while, we have made sense of some of it together, traveled through it gently, let it pass through us the way neutrinos pass through everything, leaving almost no trace, but somehow still touching. Let your eyes close now, if they haven't already. Think of the light that left those stars thousands of years ago, traveling toward you this whole time. Think of the ocean of Europa, dark and deep and never touched by sunlight, perhaps never to be visited in our lifetimes. Think of the golden record drifting through a silence so complete that there is no sound at all, not even a whisper, carrying a mother's voice and rain and the sound of the sea. Think of Triton falling slowly inward, decade by decade, century by century, patient as only a moon can be. Think of the Andromeda galaxy approaching across 2.5 million light years, its outer halo already beginning to overlap with ours. The 2 galaxies already, in the faintest technical sense, touching. Think of how the sun bobs gently up and down through the galactic plane as it orbits, drifting above the disk and then slowly back below it, a gentle vertical wave on top of its great circular journey, like a cork rising and falling on a very slow tide. Think of how, every second of every day, cosmic rays pass through your body. Particles launched from exploding stars, bent through magnetic fields across thousands of light years, arriving at last here, passing through you without your knowledge, carrying within them the chemical memory of stellar violence. You are being touched by the galaxy constantly. You simply cannot feel it. Think of Pando, the quaking aspen colony in Utah, a single organism whose root system may be 80,000 years old. that stood through ice ages and thaws and the entire span of human civilization, without anyone knowing it was one creature, not many. Think of the seeds that can sleep for 2,000 years and wake to grow again. Think of the tardigrade curled in its cryptobiotic state, patient as a stone, waiting for water, waiting for warmth, carrying the possibility of life within its tiny, dormant body for decades at a time. The universe is patient. Life is patient. Even light is patient, crossing the void for millions of years without arriving anywhere, until finally it does. You do not need to be in a hurry tonight. You do not need to arrive anywhere. You are already exactly where you are supposed to be, drifting through the quiet end of the day, letting the facts of the cosmos ease the grip of whatever today was, whatever tomorrow will bring. The galaxy is still forming stars tonight. Somewhere in a cold molecular cloud, gravity is pulling hydrogen together. Somewhere a protostar is warming for the first time, its surrounding disk of dust and gas beginning to flatten, the seeds of future planets already gathering. Somewhere, a star far older than the sun is swelling into a red giant, its outer layers beginning to puff outward. Somewhere, two neutron stars are spiraling toward each other, their orbits decaying one gravitational wave at a time, their eventual merger still 1,000 years away. The universe does not rush. It unfolds at its own enormous pace, patient and unhurried, vast beyond anything we can hold in mind all at once. You have traveled a long way tonight, and all without leaving your bed. You have been to Mercury and stood in perpetual shadow where ice persists beside a roasting sun. You have floated above the clouds of Jupiter and watched the great red spot swirl beneath you. You have passed through Titan's orange haze and hovered above Enceladus's geysers. You have drifted past Pluto and into the Kuiper Belt, out through the silent frontier where solar wind gives way to interstellar space, and then upward, out of the disk, into the halo, far enough out to see the Milky Way as a whole, and then further still, out through the local group and into the cosmic web, to the very edge of what light has had time to reach us with. And now you are coming back, slowly, gently, the way a diver rises from depth, taking their time, letting the pressure equalize, back through the filaments, back past Andromeda, back into the Milky Way's embrace, back through the halo, past the ancient globular clusters, through the disk and into the Orion spur where our sun sits quietly, back into the solar system, past the gas giants and the ice worlds and the asteroid belt, past Mars and Venus and the moon, back to Earth, back to your room, back to your body, back to your breathing. Your breathing, which is already slower than it was at the beginning of this. Your body, which is already heavier, already releasing the day. The stories of the universe don't end here. They will be here tomorrow and the day after, patient as starlight, patient as dark matter, patient as a moon slowly drifting outward across geological time. There's always more to wonder at, more to quietly carry with you into sleep. But for now, this is enough. The cosmos continues its slow turning. Stars complete their orbits. Gas clouds drift toward collapse. Light crosses the void between galaxies. Gravitational waves ripple outward from distant collisions, stretching space itself by amounts too small to feel, but not too small to measure. The universe hums with quiet activity in every direction. And you are part of it, not separate from it, not just an observer of it. but made from it. Every atom in you was forged in stars, scattered through space, gathered by gravity, shaped over billions of years into the form you now inhabit. The universe has been working toward you across all of deep time. That may sound too large to be meaningful, but there is something in it worth carrying into sleep. You are the universe taking a moment to rest. So, rest. If you're still awake, you can go ahead and watch the next chapter now. And if this kind of calm, curious wandering through science and space helps you find your way to sleep, consider liking and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time. I hope you sleep well and dream softly. Good night.